So hi everyone, and welcome to our weekly AATRN seminar. The speaker today is Tomoki Uda, and he will tell us about stability of Reeb ordering method in the framework of pospaces.
Okay, thank you for kind introduction. I'm very happy to be invited to talk here today. I'm Tomoki Uda from Tohoku University, and I will talk about stability of Reeb ordering using the notion of pospaces. Well, sorry, by the way, I have my throat is not good because these days I have a little bit cold, so I'm sorry if it's hard for you to hear me because my throat is not good. So please ask me on the chat anytime. And okay, anyway, so let's start. Let us start with a short, simple quiz. So let X be a set and O a topology, and consider partial order on X. Then suppose X is compact, and this order is total order. Then so when does this poset admit of minimum value and maximum value? So as this is a compact and totally ordered poset, it's natural to think of this poset have the boundary or the edge of this line, but this doesn't hold true in general. We need some good sufficient condition for this to be this to hold. Do you have any answer? So we need some good sufficient condition for this. So
does the partial order need to respect the topology in some way?
yes, exactly. So if partial order doesn't respect topology, for example, consider this unit interval and cut it here, and we change the ordering like this way. Then this doesn't have minimum value, right? So in such a way, the minimum and maximum value does not exist in general, but we want something that ensures the existence of minimum and maximum. And as Henry said, we need compatibility condition, and the answer is that the compatibility under compatibility condition, this holds true, and this is pospace. So here is my take-home message. A pospace is powerful, and using nice properties of pospaces, I showed the stability of Reeb ordering method. And I will show you the pospace definition later if I have enough time. But anyway, okay, let us proceed. So here is my table of contents today. So I will first introduce Reeb graphs and Reeb poset, and I introduce stability of Reeb posets in using the interleaving distance. But to show the stability of interleaving distance, to show the stability of Reeb posets using interleaving distance, we need to use some nice properties of pospaces. So I will show some of them today. So first, I think many of you already know what Reeb tree or what Reeb graph is, but let me show briefly. So Reeb tree is a topological summarization of contour plot. So we have this contour plot, and this contour plot has many nest relation of contours, right? This contour includes these two contours and so on. So this nest relation is translated into this graph structure. This is called a Reeb graph. So what about if we have only discrete data and we want to obtain this Reeb graph? So I have embedded this Reeb ordering method 4 years ago, but for the data analysis of flow data, but I will not talk the detail of flow data analysis today. But anyway, using 0% homology, this and this, and combining them, we can compute Reeb graph. So let me show. Let me talk about Reeb graph first. So let X be a topological space and F a continuous map. And X, the pair X of F, the pair of X and F is called an R space. And so R space is just a contour plot like this. And so given a contour plot X and F, we say that the connected component of F inverse A are called contours. And the Reeb graph is defined as a quotient space of this equivalence relation where X and Y are equivalent if and only if these both 2 points belong to the same contour at some level. So by taking quotient by this equivalence relation, we have typical branch structure like this. So let's say we have this kind of contour plot. We have blue mountain here and green mountain here. And this blue mountain goes here, and this green mountain goes here. And these two contours are nested by this H-shaped contour here, and this H-shaped contour goes here. In such a way, we typically have such Y-shaped graph or reverse Y-shaped graph in the Reeb graph. And Reeb tree is the case that where the Reeb graph is a tree. I mean, so suppose X is simply connected, then the quotient space is also simply connected, and that means that graph doesn't have cycles, so it's a tree. And in such a case, we call it a Reeb tree. And also it is known as a contour tree. And for simplicity, we hereafter consider only Reeb trees. And there is a relationship between merge tree and persistent homology. And I think I do not need to tell you because many of you are professional in persistent homology. So just a short comment. So we have an increasing sequence and sublevel set filtration and applying homology functor, we get this persistent homology. And this persistent homology can be drawn as a tree like this. And this is called a merge tree. So this is very similar to this branch structure, right? So we utilize this observation. So a Reeb tree counts the number of connected components of level sets. And a merge tree counts the number of connected components of sublevel sets. And we can also consider the merge tree of superlevel sets. So combining these two, it's natural to consider we can reconstruct the information of level sets. Well, but in general, this reconstruction is not possible in general, but assuming the simply connected case, this can be justified. This idea can be justified. I mean, combining the information of sublevel sets and superlevel sets, both, then we can construct the information of level sets. And here's another observation. Merge trees are ordered sets. So for example, we have this grid data. In this grid data, we have four corners like this. This four corner represents the superlevel set at level 5, right? And at the level 5, so we have four components. But if we go to the level 4, the superlevel sets look like this, right? So it only consists of one component. So this is merging, right? Four components merge to one component, and such information can be decoded. Such information can be coded into the order information like this, or taking its Hasse diagram, it's just a tree. And now I would like to formulate a Reeb tree in the discrete setting. So let's say we want to reconstruct the information of the level set at level 4, but as you see, the level set F inverse 4 consists of 4 components. It's not a single circle, right? Because we consider this 5 by 5 grid, and because although human can easily imagine that there is such purple circles, but computers does not know such intuition. So we need to consider other notion, other equivalence relation. So here we combine these two pre-orders. So here is merge tree for superlevel set and merge tree for sublevel sets. And So combining these two preorders coming from merge trees and taking intersection, we get another preorder, this one, and this is a Reeb tree. So in this case, so this point 4 and 4 belong to both sublabel set, right? These two 4 belong to the same sublabel set, and also these two 4 belong to the same component of sublabel set. Right? So it's quite natural to suppose that there exists certain contour between these 2 points. So we use this equivalence relation, right? We use this equivalent relation, and then we can construct Reeb tree. So schematically speaking, we have 2 merge trees of sublabel sets and supralabel sets, and combining them two, we obtain this Reeb poset. So merge tree of sublabel sets consist of these reverse Y-shaped branches, and merge tree of supralabel sets consist of these Y-shaped branches, and combining these two, we obtain both type of branch structures.
Tomoki, can I ask a question?
Yes, yes.
From the Reeb poset, can you recover both of the merge trees for both sublevel and super level?
Yes, yes. So because if we so if we take quotient that close the reverse Y-shaped branch, then there only remain Y-shaped branches, and it must coincide with merge tree of supralabel sets.
Ah, thank you. Nice.
Are there any questions? So I still have 20 minutes, right?
Yep.
Right.
Okay. Okay, so let me talk about stability of Reeb graphs and Reeb posets. So Silver's group have proposed the interleaving distance between Reeb graphs in the framework of sliced category of topological spaces, and they also show that the Reeb graph is stable by this interleaving metric. I mean, this inequality holds. And the convergence is also known. So here is a natural question. What about Reeb posets? So to show this, I started this research. I mean, so I want to replace this category by the category of ordered topological spaces. So before I go to that topic, let me show you the essential essential part of Silber's interleaving distance. So let R denotes Rx, F denotes the Reeb graph of F, and RYG be the Reeb graph of G, and so, and U epsilon is a smoothing functor. U epsilon is a so-called smoothing functor for given epsilon, positive epsilon, and we define the interleaving distance as follows. So d of x and y is the infimum of epsilon, where there exists epsilon isomorphism between x and y. So we have x and we have smoothed y, and we have more smoothed x here, and this says that okay, we can go from here to here and then go back here, and this matrix requires sorry. So the interleaving distance, intuitively speaking, interleaving distance measures the difference of graph structure or typical branch structures and its height structure. So, for example, if we have such graph, and then we can construct height preserving map from y to x, but there is no height preserving map from x to y because the height structure is a little bit different. So applying smoothing functor, this one, this U epsilon y has a little bit different branch structure, so it makes possible to construct such phi from x to U epsilon y, and then it can go back to U to epsilon x. So interleaving distance is defined as the minimum value of such epsilon where such height preserving morphism can be constructed. And in their framework, they deal with graphs in the category of top over all, but there is a drawback that everything is interpolated, and there is no data resolution considered by definition, because every object is continuous. I mean, so for example, if we consider such Reeb graph, but to deal with this data in the category of top over R, sorry. We need to interpret this object like this. And even if we have much higher resolution data, and we have such higher data resolution Reeb graph, once we apply interpolation, they are the same things in this framework. But we want to compare these two posets, discrete posets, and compare them. So what is the natural framework for such discrete data? And so what is a nice way to compare these two discrete difference? Also, how to prove the Reeb order method is stable in this nice distance. So here are some remarks on the tools I need to prepare to show stability theorem of Reeb ordering method. But I want to focus on this part, I mean pospace. So pospace is needed to address semi-discrete data structure and nice quotient. We also need some other tools to show our stability theorem in this framework of pospaces, but I will skip these parts today. So now finally we come to pospaces. So what is a pospace? Well, before I define pospace, so we want to take care of both semi-discrete structure of the posets and topology as well. So pospace deal with both topology and order, and it assumes some compatibility between them. And in the preceding study, continuous structure is considered by Silver's group already, but I want to consider discrete structure as well, because I want to compare data resolution much more finer. And the pospace cherry picks both benefits. So especially, so such data can be dealt with in the framework of pospaces. So here is a discrete poset, and here is a continuous poset. And actually, we need to deal with such semi-discrete structured poset. And these three can be dealt with in the framework of pospaces. So this is a definition of pospace. A poset X endowed with topology is said to be a partially ordered space, or pospace for short, if and only if the partial order is a closed subset of X squared in this product topology. So in other words, this just says that the convergence preserves the order. So let's say we have two converging sequence xn and yn, and xn is less than or equal to yn at each n. Then x must be less than or equal to y. So this doesn't hold in general, but because of this nice compatibility condition, this holds true. And this is very nice property in the pospace. By the way, I have a strong concern about the term pospace because it is a short word of partially ordered space, but it assumes this compatibility condition, so it is somewhat confusing to me. And actually, historically speaking, a partially ordered space refer to just a partially ordered space. I mean, without any compatibility condition. Indeed, some authors used partially ordered space as just partially ordered space. But after Weisstrup has introduced this notion of pospace, it's common. This word commonly used to nowadays. But because this wording is somewhat confusing, and this gives rise some ambiguity, I'm wondering recently if it should be replaced by other moderate terms such as Weisstrup space or closed compatibility condition or something like that. Okay, so this is side note. Please tell me your idea if you have any suggestion or better term or something like that. Okay, and so what is nice is that pospace can have a reflection property. So what is a reflection? Well, it is a left adjoint of our inclusion functor. So here is an inclusion functor. A pospace is a just pre-ordered topological space. So this pre-ordered topological space means we do not have any compatibility condition here. So we have a partially ordered Hausdorff space with compatibility condition here, and it can be viewed as a just pre-ordered topological space. And if we have just pre-ordered topological space, then it can transform to a pospace. So this left adjoint is called a reflection. So I call this reflection, I call this functor pospace reflection. So quotient may fail to keep the pospace structure. I mean, pospace need compatibility condition. So, but thanks to this pospace reflection, a pospace reflection can characterize a nice quotient. So this is just like a Hausdorffification. So Hausdorffification is a left adjoint of Hausdorff space to topological space, right? And actually, the construction itself is also almost same as this Hausdorffification construction. So here is some remark on non-triviality. So the compatibility of topology and order structure is difficult and troublesome in general. So we can construct many pathological examples in general. So especially taking quotient may destroy those compatibility structure. But this category of pospaces enjoys nice properties such as completeness and pospace reflection. So thanks to these tools, we can say much more about the compatible topology and order. I'll skip this part. Let me show a short example why pospace is powerful. So here is a semi-discrete poset. And here are some elements. And this edge is half open interval. And this dotted line indicates order between 1 and 2, but because 1 is not an element of this poset, so this order represents oh sorry, oh disappears. So in such case, the poset X is somewhat graph-like, but the branch structure unclear, right? So, but actually, oh, so, oh, sorry. Oh, sorry. Oh, yeah, yes, that goes okay. Well, but here we consider, sorry, my pencil is not working well, sorry.
No worries.
So here is some pathological similar example like this. So 0, 1, 2, 3, 2, 3. And so maybe I should say like this. So what is a branch structure of this poset? Well, it's still unclear as well, but actually taking pospace reflection, we get this graph. So actually, taking pospace reflection cause such nice quotient in general. So in this case, these two points are identified, and this branch structure becomes now clear. So in such a way, pospace reflection plays a very nice role in our framework. Okay, I think I do not have enough time, so I need to summarize my talk briefly. So we just replace our category by the category of pospaces, and we define the interleaving distance just same way. And then we can show stability theorem using many tools from pospaces and any other some other tools. We can show this interleaving distance stability. I mean, this R denotes the Reeb poset of F and Z, and we compare these two Reeb posets by using interleaving distance, and this distance is bounded above by this difference of input data F and Z. And here are some technical assumptions. I mean, Reeb poset trees, generalized trees, but I do not tell you the detail here. Here is a sketch of proof, but there are some difficulty in showing well-definedness of the epsilon isomorphism between Reeb posets. And such difficulty is overcome by using the pospace. Pospace is very powerful. Okay, so let me summarize my talk. So Reeb poset is a semi-discrete alternative to Reeb graph, and interleaving distance in the framework of pospaces shows the stability of Reeb posets. Okay, and here is a preprint. I showed stability in this sense, and yeah, if you are interested in my work, please look at this preprint. Yeah, thank you.
Thank you. So before getting to questions, I would ask everyone to unmute themselves for a little round of applause for Tomoki. Okay, so now it's time for questions. Feel free to just unmute yourself and ask.
I'll start with the question, Tomoki. So on one of the slides you skipped over, there was a bound comparing an interleaving distance to the Silva one. Could you explain this a little bit?
Okay, so it's just a data resolution matter. I mean, so for example, so for example, consider such poset. And on the other hand, we can of course consider 0, 1 interval, right? And let's say this is x1 and this is x2. And so in general, so Silva's interleaving distance compares everything as interpolated object. So this one is 0. I mean, this needs to be interpolated everywhere. So it is the same thing as x2. But in our interleaving distance, this x1 and x2 differs. I think this is 1/2n. Yes, 1/2n. So our interleaving distance captures the data resolution much finer. So here is a difference. And in general, this I think this holds, but actually I did not show this in the I will not show this in the rigorous statement yet. So I need to, yeah, I need to work on this as well.
That's very nice that your distance can distinguish those two examples, the entire interval versus the discrete version. So that's very nice.
Thanks.
Okay, more questions for Tomoki.
Hey, yeah. Sorry?
Okay, so I think we do not have more questions right now. I will stop the recording and then we can take questions offline. But thank you so much again for your talk.
Yeah, thank you.